Iowa grows a lot of corn, enough calories for everyone in the United States to eat nothing else. This is only possible by adding a huge amount of extra nitrogen to the soil. However, not all that nitrogen actually ends up in crops. When it rains, it leaches into streams and rivers, and then eventually the municipal water supply as nitrate, a carcinogen. The typical background concentration of nitrate is around 1 milligram per liter, but in residential water in Iowa, it's frequently over 10 milligrams per liter, the federal limit. This is a big reason why Iowa is the only US state with a growing cancer rate. It's also why state and federal agencies deploy real time sensors in Iowa's waterways to monitor nitrate levels. However, coverage is spotty, sensors break, are expensive to deploy, and many have been decommissioned following recent budget cuts. This leaves residents, regulators, and farmers flying blind in the exact locations they most need information. But what if you could predict nitrate from other sources of data? Put a virtual sensor in the river, if you will. Well, my team thought this might be possible. We wanted to know, if you know what's planted where and whether it's recently rained, can you flag days with high violation risk? What you're seeing now is the widget my team built to help explore and visualize all the data. We started with 162 sensors and then filtered down to the 85 best. For each site, we then computed the drainage basin in 3 different ways. For most sites, these 3 basin choices agreed, but for many others, they were quite different. It was important to get this right, so we manually went through our sites and picked the basins that made the most sense. We then layered crop, soil nitrogen surplus, and daily weather data onto our basins, all stitched together onto a common grid, which you see here with cells colored by dominant crop type. Here we're also displaying a graph of the sensor's nitrate and precipitation data for completeness. We then spent some time exploring the data we'd curated and found 3 big things that informed our modeling. So first, waterborne nitrate has a strong memory. If a sensor read a high value yesterday, it will likely read a high value today. Second, nitrate is highly seasonal. It climbs in April, peaks in June, falls in late summer, coinciding with the growing season of corn, as you might expect. And then third, sensing sites have high variability. Most are pretty small, but some are truly massive. Some sites almost never see a nitrogen violation, others stay consistently above the 10 milligram per liter threshold. Our finalized feature list consisted of daily weather data, stuff like precipitation, temperature, and solar radiation, annual crop data, annual nitrogen soil surplus data, geographical features like latitude and longitude, calendar information to help with seasonality adjustments, and average statewide nitrate values, giving us 68 total features. We found that grid cells near the sensors mattered far more than grid cells far away, so we accounted for this by aggregating data into near and far distance buckets and also by weighting values directly by distance. Let's talk about modeling. We tried linear and logistic regression and traditional time series modeling experiments, but these failed miserably and we quickly moved on. The first positive result we got was from XGBoost, whose baseline results at least gave us positive predictions for both regression and classification targets. Being honest about our validation during training was critical. As you can see, basins nest inside of each other, and sensors with nested basins report correlated values. To ensure we didn't leak our targets to the models during training, we kept overlapping families of basins on the same side of the test and training split. Our regression results are modest, but we still get positive predictive power. Our model explains about a third of daily variance on unseen basins. Flagging violations works much better, however. This score is the one we value the most. It tells us roughly how well our model balances true positives with false alarms, and our results are 2.4 times better than a random guess baseline. With proper tuning, we can do even better. To see what I mean, let's look at the deployed model in our widget. We drop a pin anywhere in Iowa, and it produces a basin for us. We can then run a forecast on a chosen model year, and we get out predicted regression and violation probability curves. By changing the beta parameter you see on screen, we can change the trade-off between the number of true positives we detect and the number of false alarms we're willing to tolerate. With it set to 2, we expect to catch 86% of the true positives, but we'll have to tolerate over 50% of our violation flags being false alarms. Now, this model is obviously limited. Our 85 sensors aren't enough to fully represent all of Iowa, and you can't learn everything there is to know about nitrate from daily weather data and annual land use snapshots alone. Indeed, there are other sources of pollution besides agriculture. For instance, manure runoff from livestock operations are also a big source of nitrate, and we'd like to incorporate that data in the future. There's also a feature present in our current dataset which we barely utilize, the network effects which link sensors with connected basin. We'd like to see if graph-based model architecture could fully utilize this richer structure. Nitrate predictions enable various groups to act faster. For instance, utilities can start treatment before a spike hits, farmers can better plan the application of their fertilizer, and agencies can target their funding towards areas that really need it. Now, our virtual sensor model is not going to replace physical detectors, but as an alternative to no information at all, even an imperfect prediction is a major upgrade.